Number one, to distinguish between physical properties and chemical properties. And number two, to describe 16 of the most important physical properties and give examples of each one. So let's dive in. So the first question we need to ask is, what is a physical property? And a property is basically a characteristic of a substance. And you can see here in this picture, I have all different kinds of things pictured for you. I have sand, glass, gold foil, water with rocks, some close-ups of snowflakes, and an ancient glass jar here with olive oil in it. And all of these are different substances, and they have different properties that make them different from one another. And so part of being a good scientist is being able to tell the difference between what some of these properties are. Now, each of these substances has more than one property, of course. So I'm going to get into those with you, but what I do want you to notice is that there's a difference between physical properties and chemical properties. And in this lesson, we're going to focus on the physical properties. Okay, so before we dive in, a physical property is a property of the substance by itself. Okay, so physical. In contrast, a chemical property has to do with the way the substance interacts with other substances. In this lesson, we're just going to focus on those things that characterize a substance all by itself. Okay, so I've divided these 16 different physical properties into groups, and hopefully that will make it a little bit easier to remember. So the first group that I made up for you guys is appearance, because these are how properties that relate to how something looks. So the first one is pretty straightforward. Shape, the form of an object or substance, and this can be the shape of the object on a big scale, or it could also be the shape of the object on a smaller scale. And if you'll remember back to our crystals lab, when you made crystals of different substances like alum, Epsom salts, and regular table salt, all of those crystals had different shapes. The alum was sort of like almost like a pentagon. The Epsom salts were very spiky, and so on. So those are some examples of shape. Color. So this might also seem very straightforward, something that you have been, looking at since you were very young. But let's take a little bit of a deeper dive into what color means scientifically. So when you see color, what you are basically seeing is electromagnetic radiation or light bouncing off of a substance. And every different substance, because of its physical properties, can either absorb some wavelengths of light and reflect others. So in this diagram down here, we have the different colors, Roy G. Biv, red, orange, yellow, green, blue, violet. And an object that looks blue to you is going to absorb all of these colors of light except for blue. And blue is going to bounce off, and then this is actually, that should have been a blue line right here, but the light is actually going to bounce all the way into your eyes and hit the back of your eye, which is your retina, and then send a signal to your brain saying, oh, I see blue. Now it's a little bit different with white and black. For a white object, all of the colors, because all the colors mixed together, make us see white. So this R probably stands for rainbow. All of the colors are going to reflect off of the white object, and then your eye registers that as white when you see all the wavelengths together. In contrast, a black object is going to absorb all of those wavelengths and not reflect anything back, and you see that as the absence of color, which your eye registers as black. So when you are talking about the physical property of color, we're really talking about how electromagnetic radiation either absorbs or reflects different colors, and then you see the wavelengths that bounce into your eyes. Similarly, another physical property is called luster, and this is how shiny an object appears. So when we're going back to look at some of these substances, this gold foil right here has very high luster. You can see it's very shiny. It's reflecting a lot of light back. So what luster is really saying is that the substance reflects a lot of light such that it looks shiny. So it's a little bit different than color because the color is giving specific wavelengths. and luster is just going to reflect a whole lot of light back to you so that it's going to appear very bright. A substance that is more darkly colored or has low luster is not going to reflect a lot of light back to you, so it's not going to appear shiny. All right, now here's another category that should help us to distinguish some of these physical properties. These are properties of movement or touch. And so these are kind of how substances interact to being handled. So the first physical property is hardness, and this is basically resistance to scratching. And you might remember from earth science, there's actually a hardness scale from 1 to 10, with 10 being the hardest substance known to humankind, and that's actually a diamond. Okay, so this is a hardness of 10 right here. And that means that the only thing that can scratch diamond is another diamond. Other substances are going to have different numbers on this hardness scale, and I don't know what those are off the top of your head, off of my head, but if you wanted to look that up, that would be fabulous. But I do know that glass tends to be fairly hard. It's going to be near 10, but not exactly 10. It resists scratching. And there are other substances that don't resist scratching at all, such as clay. If you took a little toothpick and tried to scratch a line in non-hardened clay, it's just going to make a line right through it. So that substance is not hard at all. Another substance is brittleness. Brittleness is how easily an object breaks or shatters. And sometimes objects that are higher on the hardness scale tend to also be brittle. And an example of that is glass, right? Because you could take a nail and try to scratch the glass and it's going to resist that scratching quite a bit. But if you throw the glass on the floor, or like my coffee mug on the floor right here, it is going to break into thousands of pieces. So easily shattered. Another physical property is called malleability, and this is sort of the opposite of brittleness. Substances tend to be either brittle or malleable, but not both. So malleability is the ability of a substance to bend without breaking when it has a lot of blunt force applied to it. And you guys know this well, because how many times in class has your Hydro Flask fallen on the floor? And it never shatters into a million pieces, right? Thankfully, because that would be a huge mess. But it often falls on the floor. And when that happens, it makes a dent, right? So many metallic objects are malleable. And you can just look at your Hydro Flask to remind you of that fact. All those dents in there are a sign of its malleability. It will bend without breaking. Ductility is closely related to malleability. It is the ability of a substance to be drawn into a wire like this. And so many objects that are malleable are also ductile, because if you apply enough force through a small opening, you can actually force it into a long, skinny wire. And the last property under this category is elasticity. And this is how easily an object can stretch and then return back to its original shape. And so the first thing that comes to my mind immediately is a rubber band, very easy to stretch out, and then it snaps back to where it was, as long as it's a rubber band in good condition, of course. All right, also, stretchy leggings, those kind of things are highly elastic. And next we have physical properties of strength. So strength is kind of how much force something can withstand before it breaks. And there are different kinds of strength here. They are tensile strength, compressive strength, and shear strength. And each of these kinds of strength is a resistance to forces in different directions. So tensile strength is resistance to forces that pull apart. So I like to use hand motions to show this. So tensile strength is resistance to pulling apart like this. And an example of that is rebar, which I'm going to write right over here. Oh, I need my pen back here. So rebar is usually made of steel, and they are long pieces of steel that are often used in construction and things like that. And they have very high tensile strength. They're not easily pulled apart. The next one is compressive strength, and this is resistance to crushing forces. And the most classic example of compressive strength is concrete, which many of our foundations of our houses, especially in California, are made of concrete, because you have this huge building that is sitting on top of it, and that concrete is resisting the compressive strength. Like all this weight is on it, and it's not crushing, it's just holding it up just fine. The last one is called shear strength, which is resistance to sideways forces. And this is something that builders of a skyscraper are going to have to be especially aware of, resistance to opposing forces, especially in an earthquake. So I like to show hand motions like this. It's resistance to like scissors kind of things, opposing forces. And if the building can resist that, it has shear strength. Okay, now sometimes we can combine some of these to make very strong materials. So I like to think of these parking blocks right here. They often have pieces of rebar stuck inside of them so that they have both tensile strength, resistance this way, and compressive strength, resistance this way, to prevent a car from crashing into something and making sure that it parks in the right spot, because cars are rather heavy, as you well know. Okay, last but not least, we have physical properties of structure. And these mainly have to do with how the atoms and molecules are put together if you like zoom in on a very tiny level. And some of these things you know already. Electrical conductivity is the ability to conduct electricity. And these are often metals, not all metals, but many metals, because they kind of hold on to their electrons loosely. Each atom doesn't keep its own electrons close to it. They kind of share like in a commune where everything, like every atom shares all the electrons with everybody else. And that means that the electrons are very free flowing. They're easy to flow one to another. And so the metal that's inside of these wires can conduct electricity very easily, because electricity is just electrons flowing through the atoms from one place to another. Closely related, but not exactly the same, is thermal conductivity. This is the ability to conduct heat. Many substances that have electrical conductivity also have thermal conductivity, but it doesn't always go together. So an example of thermal conductivity that I like to give is cast iron, which is one of my favorite ways to cook. But if I were to be, frying bacon on this thing, I would not want to touch the handle with my hand, because that has very high thermal conductivity. And if this part is hot, then so is the handle. And I'm going to need something that has low thermal conductivity, like a hot pad, to protect my hand from the heat flowing through it. Otherwise, I'm going to get burned. Another physical property is density. And we're going to be talking a lot about density in this unit and even learning how to calculate it. And this is how much mass is contained in a certain volume. So something that has high density has a lot of mass crammed into a tiny little space. Cast iron happens to have a high density. So if you think about that scene in the movie Tangled, where Rapunzel is, whacking that other guy, what's his name? Flynn Rider, with the cast iron, it hurts him a lot. It probably should have hurt him a lot harder than the movie shows. However, if she were to use something that were less dense or very low density, like styrofoam, he wouldn't have been hurt at all, because styrofoam has a very low mass per volume. So I could fill a whole box full of the styrofoam and it would be very light to carry. It would have a large volume, take up a lot of space, but weigh very little. Next, we have melting point and boiling point. These kind of go together. These are the temperatures at which phase changes take place. So the melting point is the temperature where a solid changes to liquid, and the boiling point is the temperature where a liquid changes to a gas. So I have some pictures here to show you melting point. This is some ice on a lake that is starting to melt. And each particular substance has a temperature that it melts at. So for water, that is at 32 degrees Fahrenheit or 0 degrees Celsius. You are going to need to know these numbers. But for another substance, that's going to be different, right? Because this cast iron over here is a solid, and it can get a lot hotter than 32 degrees Fahrenheit. I mean, hot enough to burn you, and it's still not going to melt. But in the core of the earth, where the temperatures are much, 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 much higher, you do have molten iron. Okay, and then likewise, the boiling point is the temperature at which a liquid changes to a gas, where it boils. So here's a picture of boiling water to give you that visual. And you're going to need to memorize these definitions and be able to recognize and describe physical properties of certain substances. And there are going to be more than one property for many things. Everything has its own melting point, its own boiling point, its own density, and it has varying degrees of strength, varying degrees of hardness or brittleness or malleability. Some has a lot of malleability, some has a little bit of malleability. So you are going to need to be able to do both of those, and